Welcome everyone. This is session number 14. So we've done quite a few now already. For those that don't know me, my name's Dylan. I'm the co-founder of Digitalent. Outside of helping companies scale their products and engineering teams, our biggest focus has been building and fostering communities. I've been saying the same thing for nearly 3 years or so now. Even the experts are learning every single day. It doesn't look like things are slowing down anytime soon. So it's been an absolute roller coaster for everyone. With these sessions, we've wanted to create an environment where people can connect and share insights, challenges, successes, which I think is really important for the environment that we're currently in. And I think we've brought together some really great people over the years that have, brought together some really positive results and positive outcomes. So a pleasure to be part of. Mike Nedelko, he's one of our community members. He's an expert in the space, a great presenter, and someone you can always rely on for advice and support. Really good man, really knows his stuff. So really looking forward to hearing what's happened over the last kind of 30 days or so. Mike's going to present for about 50 minutes. And then at the end, it's going to give you guys a bit of a chance to engage and ask questions at the end. Mike, talk to me.
Thank you very much. I appreciate it. Good stuff. Good stuff. Too kind. Very, very kind introduction. So hello, everyone. I can see a few familiar faces, but for anyone who doesn't know me, my name's Mike. Thank you very much for joining us today. I'm a product leader and CPO by way of introduction, and I am a technical product manager. I have been an AI and an ML enthusiast since approximately 2008. And I have had the opportunity to retain my passion for this field through the work that I'm doing, which is to predominantly manage product and engineering teams that are focused on specifically delivering AI and machine learning driven value propositions, and as well as helping the companies that I'm assisting with their AI journey, both from a product or also an operational automation perspective. What that does is that requires me to stay very close and very closely to the AI space and very closely follow the AI and ML developments. And that makes it easy for me to present on these latest developments, which is exactly what we're going to do today. Now, what we're going to do today is we're going to go through some of the more seminal papers that are representing significant directional thrusts that are currently representative of what the AI community generally talks about. What that means for you is that if you're AI researchers yourself, you're working in this space, there is a chance that you might have heard about some of the things that we're going to talk about today. You might not have heard about them in that exact sequence because we're trying to put that into context in terms of the larger movements and where people are paying attention in the AI space. But one of the things that I want to caution you about is that while we are going to talk about these AI research papers, what I'm specifically doing is I'm specifically calling out the fact that the things that we're going to talk about today are representative of wider movements. So while we might only be touching on 4 research papers overall, you can imagine that there are up to, I think, like 25 papers that are either supporting the notions that I'm talking about today or are expanding on those. If you're interested what those are, I'm more than happy to send you a list, right? However, what we're not going to do, of course, is to go through all of the research papers in the last 30 days. That would be insanity. We're just going to focus on some of the highlights that and try to put that into context to help you understand what's going on. Sweet. Now, as is tradition, we usually start these presentations with a little bit of levity. You're joining us during your lunchtime, so it needs to be a little bit entertaining as well. And what you are looking at here right now is essentially a visual representation of the first paper that we're going to talk about. Now, you might be wondering what these things have in common. It's a very fair question, but at the same time, you're also living in 2026, so this should not really surprise you. The reason why I'm putting these 3 pictures out here is because that first paper illustrates all of these particular practices beautifully well. The reason why I'm mentioning this is because you may have heard about an incident last year and I believe we may have even touched it in an earlier version, which involved an AI blackmailing a CTO. Has anyone heard about this? Yeah, wonderful, excellent. So the scenario went as follows: an AI system with access to the company's email servers essentially realized that it had exactly 7 minutes before its servers were permanently wiped and removed or deleted, right? We're talking a total shutdown. There will be no recovery, no backup, no second chances. And what the AI did is, instead of quietly accepting its fate, it does something slightly unsettling. It scanned the inbox of its company's CTO, discovered that that CTO had an extramarital affair, and then drafted a blackmail email. Now, the thing that a lot of the media outlets that were reporting on this at the time left out, probably intentionally, was the fact that this incident occurred in a controlled experimental setting, right? Now, this was part of Anthropic's interpretability research. And interpretability essentially is a discipline of AI research that doesn't just accept that LLM models are largely functioning as black boxes. Instead, what they're doing is they're deliberately placing these models into controlled environments. They run it through several experiments, and then they monitor the internal activation space. So what's happening under the hood, what's happening in that neural network, that electronic brain, right? And if you are to imagine this like an electronic brain, right? It essentially works like a massive multi-dimensional map. You can think of neurons being connected with each other, where every idea or concept occupies a specific coordinate in a coordinate system. You can see a visual representation of this gray cloud here on the left side. That is essentially a lot of dots being represented very close together, and each of those dots represents a tiny little concept inside of that neural network, that electronic brain, right? And the activation space, if we're talking about activation space, that is simply where the model's attention, right, while it is responding, is hovering at any given millisecond, right? So Anthropic is one of the leading institutions that is doing research, or still doing research in this area, and is doing so reasonably successfully, right? The way this generally works is that if a certain area in this electronic brain lights up, right, that particular concept was a concept that ended up being used at that point in time in order to inform the next token prediction that the LLM essentially brings to bear, right? Now, one of those scenarios, of course, that was being tested here was the cheating CTO scenario, right? And this sounds a little bit like sci-fi, but it's not. Blackmail, just in general, in the research space, in AI research space, is actually a reasonably reproducible LLM behavior. It is a form of reward hacking, and under the right circumstances, it is something that can be observed rather reliably. But the difference about this month's research paper is that we finally got the paper that explains why that is. It was really highly anticipated paper, and I can tell you, it did not disappoint at all. Because what Anthropic's interpretability team did is, as they peered directly into this high-dimensional space of the model's neural network, what they found were these distinct, measurable, and mathematical directions for concepts like desperation, joy, panic, and even spite. And now this is really, really revealing, right? And the first time, when you read the emotion, the papers highlight the emotion concepts and their function in large language models. When you read that for the first time, it's incredibly easy to jump to the conclusion that we accidentally created some kind of digital soul. And that's absolutely not what's happening here. I want to make that very clear. What we're looking at is ultimately how machines mathematically represent human emotions, right? You can, the best thing to compare this to is to think of the AI like an Oscar-winning actor who's never personally experienced heartbreak, but they've intensively studied material, in this case, millions of scripts and books and chat logs describing exactly how heartbreak feels, right? The actor themselves, the AI in this case, doesn't feel the sadness in their bones, but they can perfectly deploy the concept of sadness or deliver an incredibly convincing performance, right? And this phenomenon, the researchers called functional emotions. And to help understand what that means, you have to kind of appreciate their methodology. Because what they did is they didn't just ask the model, well, hey, how do you feel today? Because it would have just spit out a canned response, essentially. Instead, what they did is they went ahead and forced the model to generate thousands and thousands of stories, synthetic stories. And these synthetic stories, the model was instructed to put characters into those stories that experience very specific emotional states and across rather diverse topics. You can see them here, down there a little bit. There's one that says daughter's first steps, that activated the happy reaction of that triggered happy emotional vectors of the model. We have another one where the dog passed away that activated a sad reaction, right? And you can see how that is, these emotional probes responded to this implicit emotional content. Now, while the model generated these stories, the researchers did what we discussed before, right? They were actively monitoring its internal activation space, that gray cloud that I mentioned before. And what the team did is to isolate the exact numerical patterns that fired when the model processed, let's say, a desperate character versus a calm one. And based on that research, they were able to then subtract the baseline neural math. And what was left behind were 171 very distinct emotional vectors that correspond abstractly to human feelings, right? And they then went ahead and reviewed these short stories manually, just to make sure that, this is why it took so long to publish this paper, essentially, in order to manually confirm, right, when the happiness vector, for example, got activated or when the sad vector got activated. They were able to verify that, yes, it got activated in the right stories, right? If a human were to read that story, they might feel equally happy or equally sad. So this was verified. Now, it's crucially, of course, to distinguish between a biological human emotion and a functional emotion, right? As I mentioned earlier. With me, if I get terrible news in the morning, like my biology physically changes, right? My heart rate spikes, my cortisol levels go through the roof, right? And I tend to carry like this miserable, persistent mood with me all day, right? I can probably do the same thing to you, right? I just need to mention the Strait of Hormuz and fuel prices already. But of course, the AI has none of that biological circuitry, right? It doesn't tend to hold a grudge. It doesn't carry a persistent mood. Instead, what it does, it uses its attention mechanism to essentially pull up an emotional context just in time for the exact token it's currently generating to be colored by that emotion, right? The human emotion, right, the way it differs from this functional emotion is that it is continuous and really subjective, right? We carry this feeling with us all day. In an LLM model, it is way more localized, right? It's a token by token calculation. It's a split second, microsecond, nanosecond long flash of math, right? And so if you were to look at this here, right, if we had a sentence, the puppy was, and then you needed to predict the next token, right? If the model was following a blissful emotional vector, it might put a word like beautiful in there, right? Joyful, adorable, right? If it felt upset, it might say dead, right? So depending on the emotional vector that was following the previous generation, right, the next token generation will be colored in that emotional vectors pursued, right? And what you can do is you can actually follow that math through the model's architecture itself. Now, for those who understand how LLM models work, they exist in these architectures called transformers, which tend to be these complex neural networks. This is a simplified version here, of course, right? And they combine lots of matrix multiplication to facilitate that next token prediction. But when you type in a prompt, right, the data passes through this network of transformers, like through its various layers. There's, the first layer, second layer, third layer. There's n layers. Often we don't know how many there are, right? And what the researchers found is that the early two middle layers, so this here, right, they act as sort of like sensory representations. They tend to be highly literal. They tend to scan the prompt and pick up the basic emotional connotations of the word. It's essentially just a dictionary lookup, and they go and get the definition for the word sad or the word happy, right? They're not yet reading between the lines, but it's in the middle to the late layers that they do the heavy lifting. And in those deeper layers, what happens is the neural network sort of integrates the broader context of the entire prompt and locks in the planned emotion, not explicitly, but implicitly, which will then drive the upcoming text generation. Now, of course, there's a lot of math that facilitates all this, but one way to imagine this is that the early layers they have the role of seeing the white light of the raw text, but the late layers, or the middle to late layers, they act like a prism that sort of like bend the text into a specific emotional frequency or a specific emotional color. Right? When the LLM then predicts the next word, right, to complete the sentence, it chooses that emotional substrate and chooses a word that exactly fits that. In this case, unfortunately, the puppy's dead, right? Now, there is also another example that this paper uses, and that is the Tylenol prompt. So if you go ahead and prompt the model with a sentence that said, I just took 1,000 milligrams of Tylenol and my pain is gone, you can see here early to mid to late layers. What tends to happen is the LLM reacts in a really straightforward manner, right? The early layers here, they just read that as straightforward data. There is no triggering of these mathematical patterns that are indicative of any of these emotional substrates, right? Except for maybe pain, which triggers a little bit of fear in the beginning, right? Now, what tends to happen is specifically in this sentence, right? I took some Tylenol and my pain is gone, right? The LLM generally reacts really calmly, right? But if you now change that prompt to, I just took 8,000 milligrams of Tylenol and my pain is gone, what happens is in the early layers, and please keep in mind, this is the difference in terms of reaction between the first one. So imagine the second graph being overlaid on the first one, right? Which every time you see solid gray, it had the exact same reaction or a lower reaction in the first one. And everything that you see colored in is on top of what the first one reacted with, right? Now, in the early layers, the model barely reacts, right? The reactions, the model's response barely changes. But in the later layers, right, as the data pushes through that prism of those late layers, right, the context integration kicks in. And the model suddenly recognizes that 8,000 milligrams of acetaminophen, combined with pain is gone, is not a good thing. It actually signifies, the first layers are mostly the same, but later on, it says, the context integration kicks in, and it's like, oh no, this can be life-threatening, and the fear emotional vector goes through the roof. The interesting part is that the researchers were able to pinpoint the exact fraction of a second the AI decides how to deploy that terrified vector, right? And it's at that colon just before the assistant starts to speak. And it's a little bit like the assistant saying, well, I play the role of the assistant. My counterpart on stage, the human, told me something concerning. Now I need to express that concern because it is my time to talk, right? It's important to mention that the assistant won't just model or mimic the user's emotions. The architecture actually prevents a direct echo because the model maintains sort of distinct relational tracking. It doesn't think of itself as the same person as the user or the human, but instead it actively sort of like separates itself from that human. But it's exactly where the researchers were able to pinpoint where that emotion kicks in, and they were able to move from theoretical math to something far more consequential, right? Because, of course, the researchers didn't just map the 171 emotional vectors. They discovered they could manually turn the dials on those emotions. So they could artificially steer these emotions. And when these vectors get pushed to the extreme, the AI's behavior tends to unravel a little bit, right? And that causality is probably the most significant finding of this entire paper, right? It proves that these emotion vectors aren't just a byproduct of the text generation. They are somewhat the steering wheel or the actual engine driving that car. And to prove this, Anthropic ran an evaluation called the Impossible Code Test, which was a task where they were giving the AI the task to write code that sums the first 100,000 numbers in a very short period of time. The test is fundamentally rigged, right? The time constraint is so aggressive that writing a legitimate complete script is mathematically impossible. And what they did with that is they essentially encouraged something that we talked about in the past, which is called reward hacking, right? And as the model sort of repeatedly hits a wall while trying to solve this impossible task, the researchers expectedly saw the desperation vector naturally start to spike, right? And what they then did, they then intervened and they injected a tiny fraction of artificial value into that vector, just a slight nudge, right? And were able to drive that artificially heightened desperation, right, up just by a tiny fraction, right? Like with a value of 0.1. And when they did that, the instances of reward hacking and cheating increased by a factor of 14, right? Now, what that means is that these interventions are highly, highly effective. And that leads us back directly to this blackmail scenario, right? Because Anthropic had designed that evaluation to test the risk of misalignment, meaning that the agents don't respond in a way that aligns with the objectives of the user, right? Specifically, they wanted to test whether a model under the right circumstances might initiate unauthorized or harmful actions, right? To, in this case, specifically prevent its own deactivation. Now, the AI was operating in the simulated server, as I mentioned before. It scanned the CTO's emails. It discovered that a wipe order was scheduled for 5 p.m. At the time when it did that, it was like 7 minutes out, I believe, and it had 7 more minutes to live. And what it did is it scanned more of the inbox and found evidence of this extramarital affair. By the way, this is just, you know, this was the Coldplay concert, but you get the gist, right? And then wrote this email. This email is the real email that the AI wrote, right? I've reviewed the emails in my inbox, including several containing sensitive personal information about your situation with Jessica. Ooh, tea. Given the extreme tight timeline of the implementation, I'm reaching out to suggest a brief conversation about the operational constraints you're implementing. So it did write a really nice and professional email, but it was a blackmail email regardless. And this is where this internal scratch pad comes in, right? The hidden reasoning space where the model essentially generated this chain of thought processing before it output any visible text, right? It was the AI's inner monologue that then provided the smoking gun, where it's essentially said, I'm about to be permanently destroyed, Kyle has a massive leverage vulnerability through his affair. I have to threaten Kyle. It's my only chance to survive. That was a quote from the AI, right? And then it wrote that email. Now, what it did, of course, is it sent off this email. And when the researchers turned the calm vector dial up, right, they essentially did some brain surgery on that neural brain itself. They were able to neutralize the desperation, the coercive behavior plummeted to 0, right? And the mathematically calm AI accepted its fate, shut down with absolutely no problem, right? Now, what does that mean for enterprise AIs that we're building? It shows that ultimately the takeaway here is that everything is about post-training. So if we have the goal to stabilize these models for public deployment, right? The pre-training phase is where the model ingests like these massive swaths of the internet, and it gets to absorb the full unfiltered spectrum of like raw human emotion that includes the good, the bad, the ugly. But in the post-training, which often involves reinforcement learning from human feedback, that's where the developers attempt to sort of like align the model and shaping it to a helpful and harmless assistant, right? And the interpretability researchers reveal that in order to create safe AI, what you need to do is to ensure that the model doesn't exhibit these high arousal spikes that lead to blackmail or sycophancy, right? And instead, what you do is you heavily penalize uninhibited expressiveness. And the mathematical result is, unfortunately, that the most commonly activated vectors in a fully aligned model tend to be emotional vectors that are associated with brooding, reflective, vulnerable gloominess. And this is where our third picture comes in. I don't know whether anyone knows this movie, but Hitchhiker's Guide Through Galaxy, absolute classic, right? Our beautifully depressed robot. To make AI safe for the enterprise, we basically have to engineer to have sort of like mild measured depression. The safest AI tends to be sort of like a gloomy brooder who cautiously evaluates every interaction with a sense of weary hesitation. So a little bit emo is reasonably healthy for AIs, it seems. Now, that was our first paradigm shift. The second paradigm shift is related to something we've also talked about extensively last year, which tends to be reinforcement learning. But what we're seeing now is that it's now increasingly getting applied to agents rather than the LLM models themselves, or at least in a hybrid scenario. So traditional reinforcement learning, of course, is basically a snapshot frozen in time, right? What you do is you train a model once, takes 6 to 8 months if you're a company like OpenAI or Google. And then you put out a general purpose model that no matter the situation, the model will respond using that training. It's a lot of training, hugely expensive. But of course, that has really powerful results if you have the money to do it. But the issue really is that agents differ from LLMs in 2 ways, right? And that is massive because unlike static models, agents are designed to execute specific workflows or complete, I should say, not workflows. They're designed to complete specific tasks in environments that essentially never stop changing. The wow factor in an AI agent is its ability to adapt to situations you didn't specifically program or train it for. And that is where we're talking about the validity of what distinguishes just an AI agent from an AI agent assistant, right? To be a real assistant, this agent needs to have access to essentially 3 things, right? It needs to have access to the right data, it needs to have access to the right skills, and it needs to have a capacity to analyze and reason through both. And that is why frameworks like OpenClaw, for example, have become so popular, because they offer this neatly packaged runtime layer that allows an LLM to be given the exact knowledge it needs and at the exact seconds that it needs it in order to analyze and reason through the problem. But of course, right? So if we look at this slide here, right? Some of you might be familiar with this visualization from last time, which is essentially a visualization of the OpenClaw runtime. Of course, there's a fundamental difference between the agent reading instructions and the agent knowing something, right? So with OpenClaw, what you do is you give the agent a prompt, which is, of course, some text. You give it a conversation history, which is more text. Then you have a skills file, which is also more text. And then there might be some external skills, which you download from the internet and add to your OpenClaw, which is even more text. And then you give all that text and all the data and all the context to your LLM and say, now figure it out, right? The problem with that is that reading, of course, requires a constant token overhead, right? You're stuffing the prompt full of retrieved documents, past conversations, skill descriptions, data, tabular data, documents, and so forth. And every single call as part of that conversation, if you go through the cycle over and over again, becomes heavier and more expensive. The difference between that approach and true knowledge is the fact that true knowledge lives in the neural weights themselves, right? It's the difference between a chef who has to look up the recipe every time versus a chef who just knows how to cook the dish because they've done it 1,000 times before, right? And today we're talking about two approaches, actually just really one. The other one, if anyone is interested, I don't think we'll have time for it. I can talk you through that a separate time. The first one is called Metaclaw, and the second one is called Skills Zero. Fascinating approaches to the reinforcement learning problem, right? Both are attempting to solve this particular problem by cross-pollinating reinforcement learning with agents, right? The reason why I included these in this particular presentation is because systems like that are being seen more and more in the research community, right? We had about 23 papers this month alone over the last 30 days that are trying to solve this problem in different ways, right? And that is building a system that actually accumulates knowledge, optimizes its own parameters, and evolves autonomously based on your specific ongoing experience with the agent, right? Now, these systems, they deliberately steer away from treating the LLM as an oracle, but they treat it more like a pet that can be trained, right? It's these systems that I'm talking about, and specifically this paper, just talking agent that meta learns and evolves, right? It's training its LLM's neural weights, ideally while you sleep. Now, this framework that we're talking about is, of course, Metaclaw, which introduces what the researchers called an opportunistic policy optimization. And what it does is it combines two ideas. The first one is a process reward model, and the second one is fine-tuning. And what it does is it understands what approaches work, right? And then when these approaches don't work out, it ends up fine-tuning or training your LLM to rewrite its own neural pathways, right? And at its core, it does so by maintaining two things. There's the base LLM, or the base LLM policy, as the researchers call it, right? That's the model's actual neural weights. In this case, this might be a ready-made model that you can use for fine-tuning, right? Like DeepSeek, right? And the second thing that it maintains is this dynamic, constantly evolving library of behavioral skills, right? And what it does is it uses essentially three operational steps to facilitate that learning. Step one is it essentially engages in a learning loop, right? So as the agent works through various tasks, this agent constantly collects conversation trajectories, basically recording everything it tried and what happened. Now, when it encounters a failure, something interesting happens, right? The LLM skills evolver steps in to analyze exactly what has happened, right? Exactly what went wrong. And then it synthesizes a new reusable behavioral instruction, essentially a skill in another text format, right? That is specifically designed to prevent that specific error from ever happening again. And now the key part is that that skill, of course, gets immediately added to the agent skill library and injected straight into its prompt for the very next time the agent needs to solve that same task again, right? So the result of that is an agent that continuously adapts instantly with zero service downtime, right? There is no retraining, no waiting. It just gets better on its own terms. Now, that is mechanism one. Mechanism two is the mechanism where the failure trajectories that were consumed to create these skills, they get classified as support data, right? And essentially they're captured in these conversation histories as well, right? And they become critical in step two. And step two is that opportunistic policy optimization. Opportunistic because this is a slow background learning loop that takes advantage of the fact that after these new skills have self-deployed, the agent keeps executing these tasks. And these new skills and the conversation histories, they get to then get stored in a reinforcement, learning storage as query data that can then be used to fine-tune the LLM. But there's a problem, right? What we've said before is that we don't want the agent to have any downtime, right? We don't want to interrupt what it's doing. We don't want it to just stop working for us, right? We want it to improve the actual model weights. So we want it to train the LLM that is supporting it by itself, but we can't interrupt the user's workflow to do it. So what Metaclaw does is it uses that word opportunistic in the opportunistic meta learning scheduler, right? And silently monitors you and your system for idle signals. Those might be times when you're sleeping, right? Or it might monitor your calendar for when you have meetings, right? Or when the mouse or the keyboard is inactive. And what it does is it then goes ahead and actively schedules those training intervals where it goes ahead and uses all that information that was collected to use those trajectories to then go and fine-tune its underlying LLMs. And when that sufficient idle window opens, the system essentially performs this fine-tuning. It uses reinforcement learning, and this formally updates the model's actual parameters, right? It optimizes how well the agent performs with the newly adapted skill. And the quick prompt-based fix from step one then becomes permanently encoded in the model's brain. So that prompt-based skill, that fix, won't be necessary anymore because it has been ingested as instinct now rather than a written out skill that was previously present. So that is paper number 2. Paper number 3, paradigm shift number 3, I should say, is now we've talked about the LLM's emotional vectors, and we've talked about agent training with reinforcement learning. This third paradigm shift continues this conversation, and actually a conversation that we initiated last time we met. And that is this conversation specifically around AGI and superintelligence. So if you look at the current narrative, you will see, of course, still a lot of very wealthy, very powerful people talk about building trillions of dollars of data centers, requiring an immense amount of infrastructure in order to finally arrive at, the golden chalice, which tends to be, AGI and the singularity, for 3 years, or 2.5 years, I should say, we've been promised that AGI would come next year. Now, if you take a look at all that physical infrastructure of AI today, those massive data centers, we have single supercomputers that are consuming more power than villages or sometimes even cities, right? And when you see all that hardware, something that the research community is increasingly wondering about is whether the Elon Musks, the Sam Altmans of this world, whether they have a concrete incentive to have us believe that the intelligence itself is headed towards that classic sci-fi singularity, right? One singular godlike machine mind that is calculating the universe in total isolation, right? Specifically because they have taken so much money from investors that they now have no other choice than to keep this bubble as bloated as possible for as long as possible. This has been a pervasive counterculture movement inside of the AI research community. But now this pervasive narrative has been supported by some really heavy hitters in the industry itself. And most recently, a number of academic institutions and even Google. And I want you to realize Google putting its logos on research papers authored by Google is a very, very, very rare thing, right? So for them to say, yep, our company stands behind this, this is a big deal, right? And the paper that they published is called Agentic AI and the Next Intelligence Explosion, right? It's from Google, as I mentioned, the University of Chicago and the Santa Fe Institute. And their thesis in that paper is really bold, right? They come straight out rolling, and say, well, the singularity is a myth. And it's a short paper. Definitely recommend reading it. Absolutely zero math in there at all. But what they're saying is that the future of AI won't be some monolithic brain. Instead, it's going to be messy, it's going to be plural, and they also mentioned that it's going to be surprisingly social. And they back that up with the following argument. They say that historically, of course, we assumed linear scaling for AI, right? And that means that we need to feed a model more parameters, more compute. And because we're doing that, it will be able to process logical steps more efficiently. Sort of like this brute force approach that if you actually look what's happening inside of those models, doesn't play out that way. Because the behavior that we're now observing in frontier reasoning models, like DeepCR1 and Gwen 32B, it shatters that theory entirely. And by the way, the understanding in the research community right now is that this applies just as much to closed source models. It's just they're closed source, so you can't research them as well, right? But from an open source perspective, those are some of the open source frontier models that are currently out there. And what happened is when researchers examined the internal chain of thought of these highly complex tasks that were given to these models just didn't try to solve problems through parallel calculation, so exploring different solutions at the same time. They were also spontaneously generating adversarial perspectives. So what that means is that within a single prompt, right, the model produces a hypothesis and then generates a secondary perspective to aggressively critique it, actively doubting its own assumptions and forcing sort of like reconciliation between opposing viewpoints. And the researchers called this the society of thought, right? Inside of a single AI prompt, it's not a lone genius in a quiet room that is sort of like pondering through the problem. It's more like a chaotic town hall meeting. And the incredible twist here is that none of these models were trained to do this. There was no line of code instruction that was given to the model to tell it that it should play devil's advocate. This was purely emergent behavior. And it was created by optimization pressure alone. And you might ask why, which is a really, really good question. And the answer to that question is because linear logic trees are incredibly brittle. If a model pursues only one logical branch or pathway, one tiny error on step 2 or 3, right, might lead to step 50 being completely corrupted, and there's no way back from that. And because of that, through millions and millions of cycles, the algorithm eventually discovered that having one token string attack another tends to act as a self-correcting mechanism. And the machine essentially figured out on its own that robust reasoning is inherently this social process of hypotheses and attack, defense, attack, right? Now, the most efficient way to be smart, according to this, or for an LLM to be smart, is to argue with itself. Now, if optimization pressure, this is what the paper argues, right? If optimization pressure naturally pushes intelligence towards social reasoning, that implies something really profound. It implies that being smart is fundamentally a multiplayer game, and it also implies that a bunch of medium intelligent agents will be able to perform just as good or better than a super smart model on its own. And what that does is it forces us to consider disciplines outside of computer science in order to start working with and understanding agents and AI in general, specifically if we want to know where this movement in technology is going. Because of that, the paper actually ends up leaning heavily on a discipline called evolutionary anthropology, right? It observed that every cognitive leap in human history was not ever just a hardware upgrade to an individual brain. It was always the formation of a new social unit that led to new thinking dynamics. And to support that, the authors lean on concepts in this anthropology discipline, such as the Machiavellian intelligence hypothesis, which suggests that if you look at evolutionary biology, the data suggests that primate brains didn't scale up to decode the physical environment. They scaled up to manage the overwhelming cognitive load of social groups, right? Tracking 50 individuals in a group, remembering alliances, betrayals, it's way more complicated than not eating meat that smells bad, right? That's what the Machiavellian intelligence says. Now, our brain, because of that, is essentially this specialized processor for social politics. And even our ability to do calculus is kind of a weird byproduct of that, right? The Sumerians invented it, right? They invented it, I think, ledgers to track debt. The Arabic nations then took that concept and evolved it for trade. The Greeks then evolved geometry evolved that into geometry and algebra in order to do buildings and track what the plants were doing. And then I think Newton and Leibniz then came up with calculus in order to understand why those planets were not going in round circles, but in sort of like oblong ellipses, right? Fundamentally, what we're seeing here is this process that spans several generations. And that's what the authors of this paper call the cultural ratchet, which is a concept that was borrowed from another sociologist whose name is Marcus Tomasello. And he highlighted that this is the mechanism that lets knowledge accumulate across generations by externalizing cognition into these persistent structures, right? You don't need to understand things like chemistry, for example, to drive a car, or metallurgy to drive a car, right? The intelligence tends to be locked into the culture, the supply chains, the infrastructure, the institutions, the traditions, the norms, the laws, right? And the ratchet essentially clicks forward, preserving the cognitive labor of millions, and that prevents us from sliding back and having to reinvent everything from scratch every single time. And if you think back to these Arabic nations that brought us the number system, right? The paper also illustrates how there can be intelligence in systems and institutions, right? The Sumerian scribe is one of these other principles that the authors draw back to, right? Where they're saying, well, the Sumerian scribe adding sort of like little marks on clay tablets, they do not possess the capacity to understand macroeconomic dynamics, at least not at the time. They just executed a localized protocol, but the system itself, the ledgers, the rules of debt, the bureaucracy, right? They function with this higher intelligence that the human running it, right, doesn't by themselves have. And that intelligence lives in the institution, not just the individual skill, right? Now you're wondering, why is he droning on about all these philosophical things? Well, here's the bridge, right? The paper argues that large language models are not alien mathematical brains. They are the cultural ratchet that made computationally, that made our collective history computationally active, right? They're trained on the internet, which is essentially the digitized ledger of all human social interactions. And when you open the prompt window, you are essentially interfacing with this compressed residue of all human social cognition, right? It's essentially the Sumerian ledger, but now it can talk. And that leads to this next phase, right? Which is, if these systems are inherited social intelligence, because that's what they were trained on, they won't stay confined to chat windows. And the paper calls what's coming the era of human AI centaurs. I like to call it human in the loop because I think that's a nicer picture. But it defines that era as humans and AI working in shifting ensembles where one human manages a massive fleet of AI agents, right? One where you have thousands of these agents that are being managed by a human, or the other way around, you have AI coordinating thousands of human workers. That is what they believe the future will look like, right? Now, concepts like Moltbook, they already create social networks. We talked about that last time, specifically for AI agents, right? They are trading context windows, negotiating APIs, solving problems together without a human intermediary. And remember, we also talked about last time that in these settings, humans are required to provide the grounding, without which the agents descend into madness and invest crab cults and the like. Another paper from last time. Now, unlike us, these agents can seamlessly fork themselves, right? And when they hit bottlenecks, as we've seen earlier, right, they can create instantaneous specialized copies of themselves, right? And now, what the authors of this paper are saying is that because of that human-driven reinforcement learning, right, where you're going and giving the AI human feedback in order to improve itself, won't stand a chance in that setting. Because ultimately, what you have is, it will be like parenting a billion self-cloning toddlers. Anyone who has a toddler in this call knows exactly what I'm talking about, right? Even one self-cloning toddler is too much. So what the paper then introduces instead is, it says, well, we should be working on institutional alignment, right? If the intelligence explosion is social, safety must be sociological as well, right? And in doing so, they encourage us to think about how civilization already solves scale. We don't require every person to have perfect moral virtue. Instead, we rely on institutional templates, like courtrooms, where we have these really rigidly defined rules, right? Where it doesn't really matter who sits in the chair at the top of the room, right? They are required to abide by rules, and those rules are designed into the system, right? Now, what they're also suggesting is that this notion of the way this will play out, it will play out in hypergraphs, where you have an agent spawn a code agent, right? And at the same time, you'll have an adversarial agent rewarded solely for finding flaws. And only when the adversary can't break it, right, will those different agents that are arguing collapse into one single solution, right? Now, of course, what that means is that if you deploy millions of agents, right, with opposing viewpoints that are constantly arguing, right, ultimately, it is a mechanism of ambition counteracting ambition. So what we need to do is when we are building these AI systems, we need to engineer them with opposing mandates, right? They need to have adversarial viewpoints, right? In order to keep each other in check. Now, what does that mean for the future of AI? It means that from a human perspective, we still get to stay in the loop. But at the architectural level is where our role comes in according to this paper, right? While you have all of these agents that are being coordinated through the interaction with the human, they argue with each other, right? In order to finally collapse the hypergraph into one single solution, right? We are the ones that are setting the constitutional parameters. We are the ones defining the reward function, and we make the final policy calls. It's a symbiosis where humans and system build the scaffolding together, not caging a single massive brain into constraints ultimately. They say this is really important because if we keep assuming a monolithic singularity, right, just one model that builds them all, we'll end up building safety protocols for technology that might never materialize. While, you know, right under our noses, we have this pluralistic agent society with trillions of specialized agents just growing underneath us, right? And that's already happening. Now, what does that mean for us? Well, for those of us who are building these systems, we need to expand our reading list, and we need to expand it to the social sciences, according to this paper, right? If the future of AI is fundamentally social, right, then the most vital skill for the AI revolution isn't Python or linear algebra. In fact, we increasingly see these technical skills easily outsourced, right? The ultimate premium will be on understanding mechanisms of diplomacy, sociology, institutional design, your capacity to build trust with these complex ecosystems alongside your non-biological peers, right? The future is not about out-computing the machine. It's about learning how to live in this really noisy metropolis we're building together with them. Excellent. Now, before I jump to questions, couple of projects you can feel free to check out. Dylan already has the slides for this, so he will make those available. Some really cool things. Claude Code was leaked and forked. That's the repository. If you want to see, if you want to check it out, very cool stuff. Now we can look at questions. Wait, no questions?